Ladies and gentlemen, boys and girls, I hope you've had a lovely day. It's my pleasure to welcome you to this meeting of the Hartford Astronomy Group. I've moved out of the way, I beg your pardon. We've got a very full evening for you. Excuse me. We've got a very full evening for you today. We've got several speakers this evening. At the end of each talk, there will be an opportunity to ask questions. If I could ask you to wait to the end of the talk before you ask them. And those of you on Zoom, you can submit any questions you've got via the chat facility. Okay, so the first item on our agenda tonight is for Martin Weston to give us a presentation about the night sky. Over to you, Martin.
So tonight, quick talk about the night sky. Oncoming at the moment is the Orionid meteor shower. So I'll put this particular slide up because it's quite interesting. So it's going to peak about the 22nd of October. So we've got a few days, hopefully get a clear evening. So if you can get out and observe, that would be good. So the reason for the shower is because we're actually travelling through the debris of Halley's Comet that it left last time it was here. Unfortunately, we won't be coming back again until 2061. But each year we will go through where the debris of the comet is. So I also put that picture up of the Bayeux Tapestry, because that shows an image of the Halley's Comet in 1066 when it was passing by. So if you want to go and have a look, this is where what we call the radin is. This is where the meteorites appear from, but they'll be all over the sky because they're going to come across, they'll go right across the sky depending on the size of them. So to find it, it's very close to the Orion Nebula, which most of you probably know, because the famous belt, the three stars, and the main stars in the four corners, Betelgeuse, Bellatrix, and I think Rigel, isn't it? Rigel. I can't remember what the other star is on the corner. So, yeah, that's where you're going to be looking. So planets are quite prevalent at the moment. Saturn's quite in a good position. Just put a little bit of information there about the rings, because the next time, in a few years, it will become less prevalent, the rings, because we'll be edge on. We're looking at them edge on. So it's a good opportunity now to go and do some observing if you can. So I've just put a little bit of information there about prime viewing time. It's quite early. So I'm just saying about temporary disappearance. So it's quite early. I think that's on my next slide. But if you've got a pair of binoculars, go and have a look. On this image here, which has been submitted by Andy Casely, you can actually see through the moons, 4 of the moons there. So here we go. So this is the observing times. So be visible around 8:30 p.m. in the southern sky on the 31st of October, by which point the light from the moon won't cause interference. At the same time, will be visible in the east lower than Saturn before rising much higher later in the evening. So again, if you get an opportunity to go out with a pair of binoculars or a telescope, have a look. It's a very bright object, not difficult to miss. Also, Venus is about this month. But obviously, just remind you to be very cautious with Venus, because because it's inside our orbit and it's close to the sun, to make sure that any observing you do, not after the sun has gone down and not when it's still up. The moon will pass very close to Saturn in the southern hemisphere on the 14th of October, which will be observed around 10:30 p.m. in the evening. So new moon almost bookending this month. Full moon on the 17th of October. The best days to observe will be about the 14th and the 18th. So I want to talk about this particular mission. This is the Europa Clipper mission, which is due to take off. Well, it was the launch window is actually tomorrow, but whether it's going to fly tomorrow, I don't know. But the little bit of information: it's an orbiter-type spacecraft. It has 9 scientific instruments, and its target is Europa, which is one of Jupiter's moons. But we are very interested in Europa because it has a liquid ocean below the frozen surface, and it's possibly one of the best opportunities for life outside of the Earth. So I'll put a bit of information there about the Clipper mission. I haven't put the animation on there because I haven't got enough time tonight, but there is an animation on the website that you can watch, which gives you a bit of information about it. So NASA's Europa Clipper spacecraft will perform a dozen close flybys of Jupiter's moon Europa, gathering detailed measurements and investigate the moon. So it's actually 50 flybys, but it does, the flybys are an elliptical orbit, so because of the harsh gamma rays and radiation from Jupiter, it can actually affect the instruments, so they try and pick opportunities when the moon is not within those gaps of radiation. So, going to go on to a few images now. So this is the Pac-Man Nebula, taken by Steve, one of our astrophotographers. It's an emission nebula, part of a hydrogen region of the northern constellation of Cassiope, and it's a part of the Milky Way's Perseus spiral arm. So that's quite a fantastic image, I think. It's not an easy nebula to it. It's not particularly bright, so the detail that he's got there is quite fantastic. You're welcome. Moving on to another Stephen image. We were talking about Jupiter earlier, so this is one Steve's taken from his back garden in North London, so that's pretty spectacular considering light pollution and all the other problems you get. This is an image I took the other night, just testing out some new equipment. So this is the famous Crescent Nebula. But you can see there the amount of gas in the nebula around the Crescent Nebula itself. But it's actually the remnants of a Wolf-Rayet star, which is an extremely hot star that burns at an extremely fast rate. And what you're actually seeing there is the material that is cast off and is actually illuminating. But Wolf-Rayet stars don't live very long, so that will become a supernova at some point in the future, if we're around to see it. And the last image I put on, which is by our Kevin Noble, of the Elephant Trunk Nebula. This is an extremely difficult nebula to image, but you can see the dust there. That dust is being converted into stars, and behind the dust you can see the stars illuminating the edges of the nebula. So that's... At the bottom, the SI is the sulfur. These are the filters he's used. He's used narrow band filters, so 5 hours on sulfur, 5 hours on hydrogen alpha, and 4 hours on oxygen to get that image.
that tonight's speaker, Richard, has come along to give us a talk, The Hidden Secret of Starlight. Those of you members of the club will remember Richard came to us and gave us a lovely talk about eclipses. A little bit about Richard. I understand he's got a great interest in trains, yeah? And was one, or perhaps the last person to work that wonderful Zeiss projector at the London Planetarium. I don't know if any of you ever went there and saw that great big dumbbell of a machine. Absolutely wonderful. So it gives me great pleasure to welcome Richard to give us our talk this evening, and also to say thanks to Jan for giving up her singing evening to come and support Richard. Please give him a warm welcome.
Right. Now, this evening, I want to talk about problems that sciences have. One of the problems that most sciences, you can actually hold or touch the objects that you're looking at and investigating. With chemistry, you can mix up some chemicals and bash them around with a pestle and mortar, do all sorts of stuff. With geology, well, you can bang a geologist's hammer at a rock and go around various sites and dig bits up. And biology, well, you've got living things that you can investigate. Botany, you've got plants you can grow and see how they develop. But astronomy, you can't do that. The only exception is, of course, meteorites, because we can hammer those. But the rest of it is completely out of our bounds. We can't touch them. We can't smell them. We can't see what they're made of. So we can, because of course we have spectroscopy. But what is spectroscopy? What is it, and what does it do? How does it work? Who developed it? Was it a discovery that few people made? Were a lot of people involved? Now, this is a really fascinating story, and that's the story that I want to share with you this evening. So go on to our first slide, if it works properly. Oh, it's backwards. Ah, there we are. Sorry about that. You've seen the end before the beginning. Okay, so here we are. We've got a rainbow. Now, a rainbow is produced by the sun. Now, and of course, we know it's rain that makes the colours, makes the band of colours that we see. But Arthur C. Clarke once posed this problem. He said, "Why don't you take yourself back and think when people were less knowledgeable, they were smart, but they just didn't know as much? What would they think? And when you think you see an arc in the sky, beautiful arc, look how symmetrical it is. You'd think it was one or two things. Either it was man-made, which was very clever, or you would think that it was a sign from the gods." And of course, that was what they did. The story of Noah is that it does give rise to this. I mean, the story of Noah is that when God decided that he would no longer flood the earth, he produced the rainbow. We know that that's because at the end of rain, when the sun comes out, you get the rainbow. But of course, nobody really investigated rainbows. They worshipped them, they did all sorts of things, but they didn't actually investigate what they were like, what happened, what was happening there. Even the great Arabic scholar Al-Hazen, who was noted for his work on shadows and reflections, never thought about colour. And in fact, when you look at the ancient world, they didn't talk about colour much at all. To them, colour was just what it was. They didn't really think about this. They painted things, but they didn't actually name the colours. For instance, a Greek couldn't really say, "Oh, it's a lovely day, the sky is so blue today," or "Goodness, that grass looks green," because they didn't really have words for colours. It was just something you accepted, like, animals, or the fact that it rained, and the fact that whatever happened, it was something. So that was a great pity. And actually, the investigation for this didn't really start until the 17th century, when Isaac Newton did his classic experiment with the prism, which apparently he bought in a local market. And he actually projected the sun's beam onto a sheet and produced the coloured spectrum that we have here. By the way, he coined the word spectrum because it was something that was sort of ghost-like, it was ephemeral. So it actually comes from the same root as the word as spectre. So he tried to do a lot of work with this. I think one of the reasons why he was doing this too was to either telescope, because the reflecting telescope that he developed was what didn't have problems with chromatic aberration, and the other ones did. But he was the first person to comment on this and actually try and do something about it. And what he found out in the end was that he couldn't actually separate the colours anymore. What he could do was if he put a lens in front of the colours, he produced another, it went back to white light. Now, believe it or not, the German poet Goethe in the 19th century actually said, "I hate Newton because he made the pure white sun into those colours." He said, "I cannot forgive him for that." Well, it's a bit late for that, but apparently that's what he thought. Okay. Now, another guy was William Wollaston. Now, Wollaston actually lived in East Anglia. He was kind of an inventor and did various science projects. In fact, anybody remember Local Heroes with Anna Hart Davis, a series on local people that did magic things and things? Well, he was one of the programs, and he invented a method of people that couldn't draw to be able to do watercolours by actually projecting the image down onto a sheet of paper. And it's the actual first use of what we now call a heads-up display, which is used by cockpits. But he noticed that there were lines that ran across the colours, and he thought at first that they were just defining the edge of the colours. That was it. Just couldn't really do anything else about it. That's what he thought. He actually used a lens which actually helped to produce these little lines, but he didn't really think there was anything more to it than that. Actually, later on, he did, when the science of spectroscopy had developed, he did actually manage to do something about that. He actually did some work on these lines and seen the various. Is there any? Okay. So that's actually he did start working on the thing because he recognised what they were after other people had begun working. Now, so William Herschel comes into this story as well because he was the first person to try and to see what temperature each colour was, and he found that the one that he passed on the red end, which he was using as a kind of the standard, was actually the hottest of the lot, and that was how he discovered infrared radiation. And later that year, a German, I can't think of his name now, he actually discovered ultraviolet. So that was the first steps in this development. But there was a problem. This guy here, Augustus Comte, published a treatise on the philosophy of astronomy and actually on sciences. It was called, if I remember rightly, it was a treatise on positivism. But what he actually said about astronomy was actually completely negative. He said the stars are only accessible to us by a distant visual exploration. This inevitable restriction, therefore, not only prevents us from speculating about life on these great bodies, but also forbids the superior inorganic speculations relative to their chemical or even their physical natures. In other words, forget it. It's a complete waste of time. That's the end of that. Unfortunately, he was wrong. Well, fortunately, and the strange thing was, while he was making this essay on positivism, the people were actually working on producing spectroscopic results. So we come to a gentleman called Franz Fraunhofer. Now, Fraunhofer was a Bavarian. He came from a very impoverished family, and he was working as apprentice in an optician's. Now, by opticians, I don't mean somebody that makes glasses. He was an optical worker. And he was treated very badly. I mean, to be perfectly honest, as an apprentice, most apprentices in those days were treated pretty badly. But the point was that his workplace actually fell down. It was so bad. And at that time, the Elector of Bavaria was walking through and noticed that this had happened. And he thought, that lad needs a job. I can give him one. And he must have recognised his talent because he trained him up. And he became the most successful optician of his time. By that I mean optician in terms of scientific optician work, like making mirrors or lenses. And he actually produced very, very high quality achromatic lenses for telescopes. In fact, the one on the left here, this one here, this one on the left, that was the telescope that was used to discover Neptune in Berlin in September 1846, and it was built by Fraunhofer. And incidentally, we call this kind of mounting German mount. We use them all the time. That was actually invented by Fraunhofer. That was his major invention. He was a brilliant engineer as well, particularly with intricate machinery. But what happened was he noticed that when he used a prism on the sun, he got these lines, and he got fascinated by them, and he actually catalogued them. He actually produced a series where there were A, B, C, D, E, F, G, etc. But he didn't know anything about them. I mean, after a while, he gave up because, frankly, his business was making telescopes. Also, the fact was that he died relatively young. He was in his 40s. Mainly, it's thought, because of his very impoverished bringing. He didn't actually live very long. And so we come on to Father Angelo Secchi. Now, Secchi was an interesting character. He was actually a Catholic priest. He was a Jesuit. Now, Jesuits, the Society of Jesus, a lot of Roman Catholic Jesuits are scientific workers. They do work in astronomy. For instance, give you a typical example, Grimaldi and Riccoli, who mapped the moon, were Jesuits. Other people, there were quite a lot of them at one stage that have worked in astronomy. And Clavius, who actually advised the Pope Gregory on the calendar reform that we refer to as the Gregorian calendar. It was Clavius that did the work. So they're all commemorated on the moon, but they're other Jesuits. So, but he was a particular, very meticulous guy, and he was also right in the forefront of astronomical work. He photographed the sun in eclipse. He was the first person to realise or to say that the corona was part of the sun's atmosphere and not something that was produced by the moon. He also corrected a catalogue of double stars produced by FGW Struve at Pulkovo Observatory. There's 3,000 and something entries in that, and he must have been a very, 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 very good, meticulous man to be able to do this work, because Struve was very meticulous, and it was the first really large catalogue of double stars. So the fact that he could do that, and at the same time produce other material as well, and he actually started observing the spectra of various stars, and this is what he came up with, this thing here, and you can see that there's various lines in different places, and different stars, different types of stars have different lines, in various positions, and it's actually what you might call a signature. So we catalogue them as Sun-like stars, Sirian-like stars, Aldebaran, and Betelgeuse, as they were the four types that he came up with. Now, it has to be said, before we go any further, that he was doing this visually. So he was looking at the star, and he was actually seeing the colours. So it must have been a really incredible experience, almost psychedelic, but also very, very delicate, because going through a prism, that there wasn't a lot of light. But he was very meticulous in his work, and he actually did a lot of work on the spectra of stars, and he's a very important character. He carried on for many years. But we come on to these two. Now, Robert Bunsen and Gustav Kirchhoff, they were chemists. They were actually industrial chemists. They worked in Germany, naturally. And what they did when they discovered that these lines corresponded with elements. And they noticed that everything seemed to have these two lines here in the yellow. You see they're there. They actually showed how the various types of spectrograph you could get. It's a continuous spectrum. That's an emission spectrum, and that is what happens when you put continuous spectrum with an emission spectrum on top. It actually takes out the light rather than having the light visible. So that's the three types of spectra. It's the three laws of spectroscopic analysis. But he noticed particularly these two lines, and eventually they found out that the reason for this was that was sodium. That was actually sodium that was doing that. And the classic experiment, that obviously Robert Bunsen invented the Bunsen burner. Now, if you put salt in the flame of a Bunsen burner, it will go yellow. Now, I know this because I've done it myself, not in a science lab, but when I was 10, I read this. So my parents got a new gas cooker, and it had one of these gas pistols, you know, gas pistol thing with a battery in it, sort of ignites it and you lit the flame. So I got the flame and I sprinkled a little salt in it, and it went yellow. I thought, works. Tried it with sugar, but I couldn't get anything, so obviously. But yeah, so it does work. But they also worked on metals. And they found out, they managed to analyse the various metals that were in samples. Now, this was actually what they were searching for. They didn't care about whether you could analyse stars. They were Germans. The Germans had had a very bad time under Napoleon. They'd been battered and beaten and actually, frankly, completely kiboshed by the French. And they didn't want that to happen again. In fact, we all know the Christmas Carol, Silent Night. Yeah. Well, that was actually written because that was the first Christmas that there weren't guns blazing over Germany. It was just silent. So they'd obviously they decided to rearm. And the point was, cannons are really good, but if they blow up when you're putting the powder in, they kill your army. They don't go anywhere else. So what they were doing was analysing the metal, because purer metals make better cannons. So this was the whole point of their work. They kind of peter out after this. You kind of find that they're going into other things, but they're part of the big German chemical industry in producing various materials and that could be used for warfare. And they seem to have got carried away with it, because it seems to be a recurring thing throughout the 19th centuries that the Germans developing stuff for war. But so maybe you can trace it back to that. Anyway, so we now had a sort of ground base as to what a line meant. So now we could actually attribute in the sun. We could attribute various chemicals. There was iron. There was potassium. There was helium eventually, because that was discovered. There were lots of elements, and we found out that the elements were represented in. So the sun was made up of the same things that the Earth was, only in different proportions. So moving on. Come on to this guy. Now this is William Huggins. Now this year is the bicentennial of his birth. It was actually much earlier, but it's quite applicable to talk about it now, because he's an important character. Now he was actually the son of a mercer, a draper, who lived in South London, Tulse Hill, now part of South London. But the thing was that he he didn't want. He'd actually studied science when he was younger, and eventually he sold the family business. Now that seems a strange thing to do. He sold up and built a telescope, etc. What actually had happened, well, and this is quite difficult to dig out of things, but they actually were silk mercers. Now they were importing silk. The trouble was the silk was actually being manufactured in England. So the demand for imported silk went down. So he more or less sold the business from I suspect it was when his father died, because it's his father that mainly ran it. But the fact was that when he actually got interested in astronomy while he was, because he'd been interested in it for a long time, and decided to build an observatory. Well, what else are you going to do? You've got money. So he built an observatory and installed a nearly 6-inch refractor in it. Now that's money. That takes serious money and commitment. That's a big telescope. I mean, a 6-inch reflector, well, it's about that sort of about that high, about that long. 6-inch refractor, you're talking about something that's about 8 feet long. It stands on a massive, massive pillar and is an engineering job. So he looked at the stars and did various things. He was getting interested, but he thought to himself, must be something I can do. And he went to a soiree, pharmaceutical society in London, and it was Kirchhoff and Bunsen, and they were talking about what you could do with spectroscopy and how it worked. And he was instantly fascinated. And he said, this was news to me like coming upon a spring of water in a dry and dusty land. Here at last presented itself the very order of work for which in indefinite way I was longing. He was helped by William Miller, who was actually a researcher working in London on exactly the same subject. He was actually working on the same things that Kirchhoff and Bunsen had been working on. And he taught William Huggins how to observe. He taught him what he needed. So immediately he buys a bigger refractor. Optics by Alvan Clark. Now Alvan Clark, they were the top of the tree. They were Rolls Royce in refractor making telescopes in the 19th century. They were in America. They were in the northeast of America, and they produced the greatest, in fact, the largest telescope refractor in the world, the 40-inch at Yerkes, which is now not used, unfortunately. That was actually was ground by the Clarks, and so was the one at Lick Observatory, the 36-inch. So they made big telescopes, and here they are. He's got an 8-inch refractor, and he's got a spectroscope, and he starts work. And he starts producing results, and it's amazing what he actually managed to do. First, mate, he unlike Secchi, he didn't stick to observing one thing. He tried observing a lot of things. And in doing that, he uncovered a lot of secrets. First one, the riddle of the nebulae. So he's looking at this object here, which we now call the Cat's Eye Nebula, NGC 6543, nice one, easy one to remember. Now that is virtually overhead. It's in a constellation of Draco. You can see it actually. I remember seeing it many years ago with my then 6-inch telescope and pointing more or less straight up. The reason he picked that was because it was high in the sky. Because Secchi had realised something important. That the fact was that there were interferences to the spectrum caused by the Earth's atmosphere. One that was water vapour. And he had to allow for water vapour being in the atmosphere. So obviously Huggins thought the best way to do this is to do this and aim high. And he looked into the spectroscope. No spectrum as I expected. A single bright line only. The riddle of the nebula was solved. The answer which had come to us in the light itself read, not an aggregation of stars, but a luminous gas. Here you've got something that's actually incredible. From the days of Messier and William Herschel, this had been a continuous bone of contention. If you got a big enough telescope, could you have resolved stars in these objects? It was a real problem. Messier obviously didn't resolve stars in almost anything. I mean, nebulas without stars. That's his comment on a lot of things. But when William Herschel looked, he actually resolved those, and actually things like globular clusters. So it was thought, well, you carry on by extension. The bigger telescope you have, the more stars you're going to see, and therefore the better resolution, therefore you're going to see more stars. No, some things were definitely nebulae, and this is one of them. It's actually a planetary nebula, which there's a different catalogue. And to be honest, planetary nebula is a wrong word, not a good word really, because it's not anything to do with planets, and it's not really a nebula. But we're stuck with taxonomy that's outdated. Anyway, so he went on to explain over 60 nebulae, including the Orion Nebula and the Andromeda Galaxy as we now know it, and noted the difference. Some were gaseous, others were not. Well, when his mother died, he was actually grieved a lot, and he couldn't bring himself to get back into astronomy for some time. But when he did, he started working, and he also married a lady, Margaret Montefiore, and she became his assistant. Now, this does seem rather strange. She was a lot younger than he was, but the two of them actually got on extremely well, and they had a charming relationship, and they did an awful lot of work. And the thing is that a few years ago, somebody actually looked at the work that his wife had done, and they found that although he sort of went through it, he didn't actually make any changes to it. In other words, they were completely independent, but they worked together. So, and he regarded her. Unlike a lot of people in the Victorian times, they did have a very equal marriage, and so this is sort of the sort of thing they did. Spectra and radial velocities of many stars. Now, they did do that, but of course they couldn't get very accurate results for several reasons. But the composition of comets. Now, there's an interesting thought. They discovered things like cyanide in comets and other things which showed that they were actually not some kind of ephemeral ghost-like thing. They actually had a basis in reality, although, of course, to be perfectly honest, Halley had proved that quite a few years before, by showing how predictable they were, what comets could be. They also did solar spectroscopy and extending the stellar spectra into the ultraviolet region of the spectrum and using photography from 1879. So he was working with photography. Now, there's a problem here, because working with photography introduces a lot of problems. That you need the developing equipment in the dome with you. You can't sort of do what we used to do in days of film, send it to the chemist or do something else or later. You had to do it then. Also, you had to have an arc lamp projecting a spectra, because when you're doing spectroscopy, you have to have a comparison spectrum so that you can see what the differences are. It's very important to have that. So he had an arc lamp in there with him, producing. He also had the chemicals for developing the plates, etc. Don't forget plates. He used dry plates to do his work. But can you imagine what it must have been like in a dome like that, working in the dark with all this stuff? I mean, I know they always say to you, when you're building an observatory or a darkroom, always make it bigger than you think, because you'll stumble if you make it too small. But can you imagine working at the eyepiece of a telescope and doing all this sort of delicate stuff, and also having trays of chemical to develop the film or develop plates? So it was really, really tricky stuff that he was doing. They also collaborated with other astronomers. Now, this is a first. They began, because mainly the European astronomers talked to other European astronomers, but they didn't. They covered Angelo Secchi in Rome, Hermann Vogel in Potsdam, Edward Pickering and Henry Draper in Boston, USA. Now, we're going to come on to them in a few moments, and Henry Draper particularly. And the funny thing was that they were in correspondence, and William Huggins used to buy the plates to send to Henry Draper, because the ones produced in London were better than the ones he could get in Boston. So there's a thought. Now, to come changing the subject just slightly here, Saturn's rings. Now, we're talking about Saturn. Jack was saying about Saturn being nearly edge on at the moment. I saw it a few nights ago myself, and it's hard to tell the little gap the hands say at the moment. It's pretty close. But there was a big argument about what the rings were composed of. And one of the things that William Herschel actually thought that Cassini's division was actually a ring of mountains that went round, and then he realised that that wasn't true and it must be a gap. But nobody could actually prove that there was a gap in the rings, because there's no way of proving it. So there was a competition, and the guy that won this competition was the Scottish mathematician James Clerk Maxwell, who proved mathematically that the rings of Saturn must be composed of small orbiting particles, as no solid or liquid ring could be stable, which is true. Something that a lot of people wouldn't know about William Clerk Maxwell, but he actually produced the very first colour image. What he did, he took pictures, took negatives with using filters. He took three negatives, converted them to positive. They used red, blue and green filters, and then he projected the result from the positives onto a screen. And there, lo and behold, was a colour image. What do you think that colour image might have been? Bearing in mind he was a Scotsman. Tartan. Yeah, he actually got a piece of tartan. So that was the first colour image. He just demonstrated it to, I believe, the Royal Society. But that's another connection with him. Very, very clever man. Sadly didn't live very long, but he was a very clever man. Now that actually, in 1859, in very elegant use of spectroscopy, Professor James Keeler of the Allegheny Pittsburgh Observatory in the USA proved Maxwell's solution was correct in 1895. What he did, he put a slit across the rings and actually took a spectrum of the various bits and showed that there was a redshift on one side, a blue shift on the other, but it was inclined. It wasn't a straight redshift. So in other words, the rings were not solid. They were actually made up of individual particles. And we would say today they were describing Kepler motion. In other words, they were rotating separately. So that was very clever. Also, another story about him. He later went on to Lick Observatory up in California, and there he worked with Edward Emerson Barnard. Now, Barnard's story is a rags to riches story. If ever you get a chance to read the book, there's a book about him. Very, very clever man, but abject poverty when he started for much of his early life. But he went on to be one of the greatest observers of comets, kept finding them. And he also introduced wide-field astronomical photography to the world by actually producing beautiful pictures of the Milky Way. So he went from one thing to the other. Very clever man, died in 1923, so that's roughly 100 years ago, roughly. But having worked with him, one of the journalists used to like to have stories about the life going on up in Lick Observatory. So one of the journalists said to him, "Look, you must have some stories about this guy Bernard Barnard. I mean, he's a strange guy." So they cooked up a thing where they invented a machine, and because by that time they knew the bands of the spectrum of a comet, they made the story that in the paper that actually Barnard had got a machine that actually had a photoelectric cells that print when the beams from these particular elements hit the selenium, it would trigger a bell and wake him up, and he'd go and discover the comet. Of course, it was absolute rubbish, but it fooled people for quite a long time, and eventually people realised, and Keeler said, "Well, it's just a friendly joke, really, nothing much." But people said to him, "Well, the reason we didn't believe it was that the way Barnard works, if the sky was clear, he would not have been in bed. He'd been out there observing, and if it wasn't clear, he'd be pacing up and down waiting for it to get clear." Now we come on to the Draper catalogue. This is an interesting bit. this in Boston, there was the Harvard College Observatory. Now it sounds posh, very, very posh. Harvard College Observatory. It wasn't. It was run by Edward Pickering on a shoestring. In fact, the only reason that it kept going was that Pickering had to keep going round, shaking the tin with his various moneyed friends in the high society of Boston to keep it running. So really, that wasn't very satisfactory. But that was the way it ran. In fact, he did virtually everything. In fact, sometimes he was the last person to lock up at night and had to, at one stage, even clean the toilets. Doesn't say a lot, does it? In fact, it's what Americans would call a dog and pony show, which is a pseudonym thing that they used to use when for about carnivals, circuses that sounded a big name but had very little acts. And this was a bit like that. It was a kind of dog run on shoestring. But his great friend was Henry Draper. Now, Henry Draper was a doctor, very eminent surgeon in Boston. He went on long trips. He was an explorer, and he was fascinated by astronomy. And he was trying to complete with his wife the Henry Draper catalogue of spectroscopy of star spectroscopy. Well, he came back from a Midwest tour, and there was a dinner to celebrate his birthday, and also the fact that he'd returned and he was now retiring, and he was going to devote his life to astronomy. Well, he was very animated at the dinner, but nobody saw him eat anything. He went to bed, had a bath, went to bed, and that was more or less it, because he never got out of that bed, and 5 days later he was dead. His wife, Elizabeth, was absolutely grief-stricken, but the one thing she wanted was his catalogue of spectra to go on. And so she went to Pickering, and Pickering said to her, well, I'll do it, but the only thing you have to do is you're going to have to provide the money for it, because we haven't got the money. Now, he was also had a lady who worked with him. Now, she actually came from Scotland. Her name was Wilhelmina Fleming, and she came to Boston with her husband, and she was pregnant at the time, and they were going to set up a life together, but he ran off and went to the California gold mines, leaving her alone. So she worked as housekeeper to the Pickerings. In the end, Edward Pickering thought, well, she's very meticulous. I think we can do something. And she actually became a real expert on spectral analysis. She could actually work out what elements were present and a lot of other things. She also kept the plate stack up to date. The lady on the far right, this is Annie Jump Cannon. She was one of the people that worked with again, a highly trained mathematician and physicist. Being a lady, because he tended to have ladies working with them. The reason for that was that they were cheaper. But, I mean, people have said, oh, he was this, he was that, he was that. But he wasn't, because actually he wasn't really even paid a salary. He worked harder than anyone else and virtually had no money. If he wasn't from a wealthy family, he wouldn't have been able to do it. So in actual fact, they all worked very, very hard. And they analysed plates taken by this observatory here, and the plate stack is there. This is where they kept the plates. This is the observatory in Boston. In fact, we've got a better... No, maybe not. So you've got the observatory here. They also have one in Arequipa in Peru. Oh, God. Where plates were analysed. So this is Annie Jump Cannon working at the light box. Now, on the left there, on the right, sorry, you can see all these little smudges here. They're individual spectra, because what they did was put a diffraction plate or a prism over the top of the objective of the telescope, which then made individual spectra of all the stars. It's quite a common technique used up until quite recently for cluster dating, because you can get the spectral types of the stars of a group very quickly. But she was analysing all of these, and the idea was that they were going to make up some kind of evolution of the stars, or a catalogue which had a beginning and an end, rather than just saying, well, that one's that one, that was that one, brighter than that does this. So the idea was to present a uniform field that ran down from one end to the other. Well, actually, they did achieve that. This is Annie Jump Cannon actually working at the observatory in Arequipa in Peru. There's the plate stack, and there's the big telescope in Boston being used for doing stellar spectroscopy. Now, this brick building still exists. Now, this was Edward Pickering's pride and joy. He actually made it like that because he wanted these plates to last for a very long time. And in fact, I read in Sky and Telescope a few months ago that they've just finished digitising the entire lot, and there's thousands. There really are. It's a stack of plates. So from that, we come to this. Between Annie Jump Cannon and Mina Fleming, they created a sequence that we now call the spectral sequence. They put them in order, working out what abundances were in each type and how they in each type and how they changed through going to different types. And what it actually is, they found out, is it's a temperature. It's a temperature chart. Hottest one's at the top, coolest one's at the bottom. And this is where we get O, B, A, F, G, K, M, and M. Different types of M. This is where it comes from, because the original thing read A, B, C, D, E, F, G, but they found out it didn't really work, and they had to, several of the things weren't really much use. So they actually decided to that they had to swap things around, and rather than swap the actual designations, they actually just changed them into that kind of order, so that it's an actual order with the same numbers. So this is it. This is what we use. The mnemonic, which incidentally wasn't invented at Harvard, it was somebody else in another college that came up with the "Be a Fine Girl, Kiss Me Right Now" or Guy. And incidentally, older people might remember that it did actually go on a bit longer because you had R and N originally, but that was realised that they were not actual stars that were different in temperature, but they were because they got carbon atmospheres, and carbon makes a star, and it should be for its spectral type. So R and N and the other ones were left out, so we haven't got the right now of it. So this is the kind of figures that they had to work on. You can imagine this took years, and that led to the creation eventually of the Hartsprung-Russell diagram. It was developed independently. That's what's not often realised. The two people, Ernst Hartsprung, was, if I'm rightly, Danish, and he didn't really realise that William Dorris Russell, was actually doing work on the subject, but they came up with independently this idea of a temperature scale up here and the type. So absolute magnitude and type. So if read it ranging from the hottest to the coolest. And this is the main sequence. Now, what astronomers have been trying to do was they tried to plot the evolution of a star. Now, the trouble was they didn't know what was actually powering the sun. They had no idea. They first of all tried coal, and then the geologist said, rubbish, that doesn't fit the geology of the Earth or anything else. Then they tried, well, maybe it's contracting, maybe the sun's contracting. Well, no, it wasn't. But they hadn't got any, so they were actually looking for a path that led from one end to the other. In other words, starting off this here and then working all that way down. But eventually what came out through nuclear physics and all the other things was that stars join the main sequence, as it were, based on their mass, and then they go along, travel along a bit, then they come off, again dictated by their mass. So each star only travels a certain amount of the main sequence. But that was unknown, and all of this later was developed by people that were, instead of dealing with the very large, the universe, they were dealing with the very small. In fact, that of course is the atomic physics. And all the work in the 20s and 30s was based on that, and to come to our knowledge of nuclear fission and nuclear fusion. The pity was it led immediately to the atom bomb, but it also led to better ideas as to what runs the sun. So that was the work of Harvard, amongst other things. The Henry Draper catalogue did get finished, and the stars on it are always noted. Now, one of the things that prisms are all very well, but they're not very efficient in separating the light. They're inefficient because they're differential refraction. So if you use this was done with a simple. This is done with a simple CD and a light. You can see that the colours shining a light along them actually produce the spectrum. And this is a modern spectrometer where you've got the collating mirror line coming down here, diffraction grating, then a mirror to revert to focus it onto a detector. So that's the modern design of, although that this is now outdated because of course they don't use this method either, but this illustrates the modern spectroscopic work that's done, and you can actually separate wavelengths much better using this system. Okay. Now, in the First World War, this guy here, working at Flagstaff, Arizona, Vesto Slipher, began the study of his spectrograms of the spiral nebulae. Now he noticed that they had a slight amount of shift, movement of the lines towards red. That all of them did, but the fainter ones exhibited a greater shift. He published his results in 1915, and it met with silence. Why was that? First World War was a good start. Second thing was that he was working at an observatory, the Lowell Observatory. Now, they had a bad reputation due to the, first of all, Lowell seeing all the canals of Mars. So really, this telescope was actually made to observe Mars, and they were using it for other things now. So it didn't really strike home until a few people began sifting through papers after the First World War. One of them was Edwin Hubble, who himself was in France during part of the First World War. And when he came back, he began to look at this, and he used the HCO catalogue and Slipher's discovery, and was able to show that that was correct. Eventually, he proposed that as a yardstick. And that's where all that came from. That came from that guy. I've not really known about much these days. They very rarely mention him, but he was an important person in that particular. Right. Well, I've taken this subject as far as I want to, because I think that once it's starting to develop now and the ball's rolling and people are beginning to develop results and papers in scientific magazines, and you're getting people like Gamow and Berta and others that were now working on the physics of this. But I want to bring up one thing. There's other things that were detected. First white dwarf detected by Mead and Fleming from its spectrum, 1910. Spectroscopic doubles were discovered by Antonio Mori, who worked at HCO for a time, the Visar and Alcor. But the big one that is, and also of course much later, the first exoplanet discovered using spectroscopy, quasars. Now, they were taking a picture of what looked to be a spectrum of what looked to be an ordinary star, but it had a very curious flickering motion. Now, in fact, one of them was actually on the VSO's list of stars to monitor, but it didn't work. They couldn't. It was too up and down, too flickery. So they took a spectrum, and immediately nobody could understand it because it was just gibberish. And in the end, it was Walter Bader, amongst other, Martin Smith, that discovered with Jesse Greenstein that if you actually move the redshift along a bit, it did fit. So these were cosmic beacons, gigaparsecs away from us. Now, there were people who didn't believe that. They said, well, surely this has just come from, they can't be. I mean, how can they be bright like that and sort of at that kind of distance. They can't be. They must be stuff that's been shot out at relativistic speeds from our galaxy. One of the people who did believe that was guy that actually gave a talk. Trying to think, anyway, not important, but there was a big controversy about this. Was the cosmological redshift correct, or was it not? Could it be that they can interspect into it doesn't exist? But it did, and it was only that the equipment at the time couldn't actually resolve what these things were. And of course, now we know that they're the jets from super black holes in the middle of galaxies, and that's actually what you're looking at, and that's why they flicker, because they knew that the whatever it was had to be small, because it couldn't flicker. If it's a big thing, the flickering would be cancelled out. So it must be something very small that's producing this for flickering to actually appear like that. So it had to be small and very distant, and eventually it took years of work before they finally came up with the answer that in fact, what you're looking at is something very, very distant. And there's the proof of all this, the big debut of the Webb telescope. And this is some of the references that I had to use. I actually enjoyed it very much. A couple of books that you might enjoy on that are The Life and Times of Edward Emerson Barnard. It's a great book. You get it in paperback. Sky and Telescope, various issues. Life and Times of the Telescope, yeah, that's a good one. Planet Saturn, yeah, that's out of date now. Stars and Their Spectra is a good read too. And of course, the one that I got a lot of that stuff from, which is the Glass Universe, which is a book by Dava Sobel. That's interesting. Anybody can read that, and I'd recommend ladies to read it, because believe me, you've got a treat. It really is a good book, excellent book, very well written about the lives of the astronomers. And with that, I'll leave you to think. Thank you very much.
Richard, what a fantastic talk that was, taking us all the way along there. Absolutely brilliant. It would be very unusual if we hadn't got some questions, so we'll pop the lights on so we can see those of you at the back as well. Okay, so any questions?
Well, my question is coming from... Okay, it's from a much more scientific background, because I'm very curious. Because one of the things you've mentioned, I noticed that they would take spectroscopic lines of multiple stars on a plate.
Yeah.
If, let's say, there were two stars that were parallel in line, wouldn't there cause an interference when two stars intersected? Wouldn't their spectros...
That's true. That's true, but this is a technique that was used for cluster dating. The reason what they did, the first indication of this, using this multiple spectra technique, once it had been used on that project, they used it to do analysis of the Hyades star cluster, which is the star cluster in Taurus, that's got a lot of range of stars. And what they did, because they very rarely find they overlap each other, and if they are, they're very faint. So they're looking at the main sort of stars that you can see. And what they did, they could define a turn-off point where the brightest stars had turned off off the main sequence. Because what they were trying to do was to date the clusters, date the ages. So they were working out what the oldest star was in the cluster, amongst other things, and that was the way they did it. So yes, the technique works, but I think the fact is that because you're looking at telescopic image rather than they didn't use it as an all-sky camera, so there was sufficient distance between objects for the resolution to be correct.
Okay.
That helps.
Thank you for your answer.
Okay, another question?
Okay, so Peter Jenkins asks, a fascinating and enthusiastic explanation of a complex technology. Thank you. The better our telescopes become, the more spectroscopic data we'll be able to collect. How is artificial intelligence being integrated into spectroscopic analysis, and is it going to revolutionize the accuracy and efficiency of interpreting the data?
Good one. I don't know the answer. I don't think anybody does at the moment. I mean, the best analysis recently has been the Gaia and earlier the Hipparchus missions that have produced a huge amount of data. Maybe AI could be used for disseminating that information and actually working out, producing models, etc. Because it's a huge job. I mean, they've got a big place in Cambridge, in this country, which is analysing the data from Gaia. So that would be a possible, I would think. But other than that, I'm edging into the unknown here. Me falling over the unknown as well. Okay, I hope that helps.
Thank you. Any other questions from the floor?
I actually don't really know how to phrase this question because I think you'll need a long talk to explain it. With nebula, or certainly with the planetary nebula you pointed out, you said there was no bars in the nebula which showed it wasn't a star. But given that the gas is being heated, I would have thought there would be a spectrum to examine there. I didn't quite understand, or maybe I just totally got the wrong point.
No, I don't think so. What you've got there is an emission spectrum, which is the bright lines. This is not like for instance, if you're taking a spectrum of the sun, you've got the continuous spectrum at the back, and the dark lines, which are the absorption lines, taking the various wavelengths of light out of those particular areas. But with emission spectrum, it's different, and that's the thing. Is I think it's one of these things that, I mean, there are differences between planetary nebulae, for instance, and the normal nebula, which is a cloud of gas and dust. So it's a bit difficult because they produce different spectra, but it's still going to be emission.
But there's no absorption, just emission.
Yeah, that's it. What you're looking at is the emission from the actual material, rather than.
But the sorry, I don't want to drag it on, but the way I'm thinking of this, the gas is being heated. I mean, with the planetary, it's been heated by the star in the middle.
Yeah.
I would have thought there would have been some absorption, or there just isn't. It's just
no, because it hasn't got the normal. Because it's not the star is actually really, really small in the middle, and it's putting out a lot of UV as well, which is actually making the gases fluoresce.
Right.
That's what's really going on in the planetary nebula. But that's why we see them.
Okay. All right. Thank you. I think I got some reading.
There's a classic bit in the film with Eddie Redmayne playing what's his name? Hawking, where he takes his girlfriend to a disco and explains the light on the black light is actually what comes from the stars, and he said, I like knowing that fact, and I thought, yeah, very good. Because he was saying how that's why it makes your teeth white and stuff like that. Anyway, thank you.
Okay, any other questions? Okay, no, any more from the internet?
No, not good.
No? Okay, well, I think all of us have had a really enjoyable evening and learned so much about it. So thank you very much indeed for coming along and coming along at short notice as well. I'm sure all of us here would like to say thank you.
Giving up earlier.
You're very welcome. Okay, we now move to another part of the evening because we've got some very exciting news to be shared with you. So I'm going to ask Richard and Alana to come down and join us at the front here, and I'm sure you're going to listen to this with great interest.
Right, what are we doing here? Not quite sure, actually. First of all, thank you very much for a brilliant talk and for filling in. And secondly, what are we here about? I'm not sure, perhaps some of you have seen on the newsletter at the bottom, there was a piece adding on about starting back something that our club's been missing for a long, long time, pre-pandemic actually. Before the pandemic, we used to have moments when, weather permitting, after the talks and whatnot, we would go outside at the pub, set up scopes, bring scopes along, and we'd set them up and actually observe the night sky. Unfortunately, the pandemic killed that all off, and also, unfortunately, moving here has also nullified that, unfortunately. Brilliant for talks, but, not a very good place for actually looking up at the sky. So, Alana, and with help from our good sir, have been trying to put our heads together as to trying to get back to observing and getting the observing part of the club going again. So, we've been working hard, and we have managed to basically set up a place at Bramfield. Now, some of you might have been there with my telescope doesn't work issues that we have, where people have got telescopes, they don't know how to use them. We've had a few workshops there where we've tried to help out. The site is very helpful. The people that run it, the hall, are also extremely helpful. And with that, we have basically got Bramfield now as an observing site where we can go at, I'm not going to say easy notice, we have to give them notice. One's because of security issues, and secondly, we need to make sure the hall's not being used, because obviously there'd be lights and there'd also be a vehicle parking issue. But generally, the site is ready for up and running and going. The thing is, we have to give them notice, and we have to think of our own security too. So it's not a case of just rocking up there. It has to be organised. And with that, we've decided it has to be organised with a committee member and at least one other member. So that there's security, because the one thing you can't do, if you suddenly need, like I just needed, you can't leave all your kit sitting there and somebody turns up and says, oh, this is handy, nice box of eyepieces, goodbye. So for our own safety and our own safety of our own kit, there needs to be 2 people. Anyway, that aside, it's more or less set up, ready to go. The lady's just waiting for the phone call from me to say what night. And that's going to be the other issue, unfortunately. When's it going to be clear? Now, our biggest enemy, unfortunately, is the weather with this sort of thing. So we've kind of decided that we would try to do it once a month at least, depending on the availability of the site, the availability of a committee member, and one other member. And then whoever else wants to come and join and enjoy the, I'm going to say party, but it won't be a party, but enjoy the experience of actually sharing experiences again at the eyepiece, explaining to people how to help them get round the sky, and bring that part of the club back that's been missing for so long. So, yeah,
but you can't see cloud with us too.
That's right. And you can't see it from a darkish site.
What do you mean you don't want to stand in a dark field with me and Richard?
Go on, it's pretty good, isn't it, really? Anyway, so that's basically what it is, to bring that social aspect of it back, the laugh, the fun, and the camaraderie of it that's all been missing. Now, at Bramfield, there's a little issue with the car parking. There's about 12 spaces in the car park, and we think we can probably get away using the hall car park as well, which has got about 4 or 5. But I'm not expecting hundreds to turn up. However, we do obviously need to work out how it works. Now, this is the one that's been a bit of a headache, but Alana has very kindly set up a WhatsApp group, and a few people have joined that and got going. A few people have also filled in the little red box at the bottom of the newsletter, and also it's now on our web page on the front, where you can actually click on a link and fill in the details to whether you'd like to come. Now, it's not a life commitment. We're not saying once you've signed, you're there every week. It's as and when you can, if you want to. Simple as that. We don't want to put hard commitments on. We would just like to know yes or no, and so we know of numbers coming. So basically, that's what we're trying to set up. Alana's got the WhatsApp group going, so you can speak to her
Yeah, if you want to, you can either come and find me and give me a number and I can add you like that, or you can email me either from the website. If you go to contact us and click on secretary, it will come to me. Or if you're good at remembering, hit secretary@heartsastro.org.uk. You can email me with your phone number and I can add you that way. We're also going to do, for those of you who haven't got WhatsApp or don't want to be on a WhatsApp group, you can email us. We're going to put that email on the website somewhere. Yes.
Yeah.
That is our plan, Alan, that we're telling you. And then we'll try and email you. We think, obviously, WhatsApp's a lot quicker because if weather changes quickly, we can just bulk out a quick text to you all. But obviously, we appreciate that not everyone's got WhatsApp or maybe doesn't want to get it or for whatever reason. So, yeah, we're giving you 2 options. But, yeah, come and find us and we can add you to whatever communication portal you want to be on.
Yeah, so those that, obviously we understand that some people are a bit sceptical about social media, WhatsApp, Facebook, this, that and the rest of it. So for those people that don't want to do WhatsApp, I'm willing to do emails, but obviously I don't want lots of them because otherwise if we have to cancel at short notice because suddenly, the weather forecaster man's got it wrong, surprise, surprise. I don't want to be sitting there for half an hour trying to type out all things, copy, and send them off that I've only just learnt how to copy. Otherwise, I'll be individually typing each one out. So that's what's going on. All I can say is keep an eye on the website. You might suddenly find there's a new heading at the top, depending on how busy somebody is. And then we'll be able to respond with a proper, a bit like the secretary, there'll be a HAG observing bit with our names on and whatever, and you can contact us and we can get things going. So it's still in early stages, but I'm really hoping that maybe by the end of this month we might get our first up and runner with a bit of luck. Anyway, sorry to bore you, but as I say,
Yeah, we look forward to seeing you there.
Yeah, any questions? No?
Sorry, could you repeat that for the people on Zoom?
Is there access to mains power supply there?
There
for us
isn't,
to derive
unfortunately.
12 volts.
No, you've got to rely on your own battery packs or whatever. Yeah, unfortunately, yeah. Although I've been given access to the hall, it is only for the toiletry facilities. And I can't go into the hall itself. I've got a feeling it might be alarmed actually, so I can't go in there and actually plug in. We actually won't be at the hall. We'll be a bit further down in the field. Although if it does get too wet or slippery, I've also been given the okay that we can use their hard standing area.
That was my next question.
Yeah. So we're not going to be sitting there going,
Yeah.
my telescope's sinking. So if it does get too wet, then we will actually move up onto their patio and hard areas.
Thank you.
Thank you. Another question?
It just depends on how well the ground drains. The bit where I'm looking at is a little bit of a slope, but yeah, it depends on how wet it is. But then if it's that wet, we probably won't be going.
If I remember rightly, there's a pub nearby as well?
There is, yes. There's the Grandison Arms pub. Now, we were going to use that as a kind of toiletry facility and refreshments. However, the lady that runs the hall politely informed me that actually during the winter months, they often shut at 9 o'clock because being so local and so remote, they don't have a lot of clientele. And in actual fact, on a Monday, they don't open at all. So that's we sort of said, well, that's a bit iffy then, because if somebody wants to go at 9:30, where do they go? So that's when she kindly offered me the access of the key to the hall, so that we can use the toilet facilities in there. So the pub is there. You might have to dash to get a drink. But again, maybe if we can strike up a bit of a rapport with them, maybe that might ease a bit of the car parking issue, depending on how numbers come along, or it grows, you never know. And obviously the people on Zoom as well, I'm not leaving you out. Please feel free to click on the links. You'll be added. That's not a problem at all. So, it's not just for the people in the room.
Okay, any other questions? Nope. Pop down here. I think one of the things we also discussed was there were certain nights that it wouldn't.
Yes, yeah. At the moment, although I'm not sure about this because she then said about a Saturday night, at the moment the hall have requested that it's not a Saturday or Sunday night. Now, most of the time it's because the hall is actually occupied on the Saturdays and Sundays by their own village people for certain events, like yoga and things like that they do, which, you know, you might be interested in. You know. But that aside, I don't think it's so much the fact the hall would be up and running, it would be the fact the car parking issue with the least number of cars, if they suddenly turn up. And there's one other night where I know they use it for their parish meeting, and that might also be a night that we might have to avoid. But as I say, it's all going to be dependent on the weather, how we can get it up and running and finally get it going. So, but I'm really hopeful that we can.
Brilliant. Okay, anything else you'd like to add to
I don't think so, but you know, as I say, any questions you can either ping it us or ping it through us. And
send them through, and we'll get them forwarded to the right people. I think it's a wonderful opportunity, and especially if you're quite new to it and want somebody to help you out a little bit with what you're doing. So don't be afraid to come along and join in and have a lot of fun there. So thank you very much indeed for all the work you've done on that. Brilliant. Thank you. Okay, it's always lovely when we can sort of move forward with new ideas like that. Wonderful. Okay, so moving on then, just a couple of reminders about future talks. The first one to tell you about is the next HAG meeting, the astrophotography section. They've got Dodie Reagan coming via Zoom all the way from Texas. So that's going to be an interesting one. But the important thing to stress is that we've moved the venue to this building, it's a room upstairs, and because of other logistic problems that have occurred, the Gain University have made a room available to us. So that's on the 15th of October. That is on the website as well. Our next meeting here actually follows on rather well. Do excuse my croaky voice. It's not contagious. We've got a talk on November the 13th by Richard Conan Smith, So Simple a Thing as a Star. Now, I think the name there probably indicates there's no such thing as a simple star, but this was a quote from a book written in 1926 about learning the simplicity of a star. Well, I think we've moved on nearly 100 years since then and found that they're a little bit more complicated. So if you want to come along to that, that's going to be our next talk, and that's November 13th. So that brings us to the end of the meeting. I'd like to say a big thank you to all of you for coming along, making it such a wonderful meeting, and especially to Richard for filling in at the last moment, and to Jan for giving up her singing evening. And of course, a big thank you to all the technical team and everybody on the committee who've been working like mad to try and make the meeting as smooth as possible, despite one or two hiccups. Well, that's life, isn't it? We put up with that. So, on behalf of the Hertford Astronomy Group, thank you again for coming along, and I hope you have a safe journey home. Good night.